Good afternoon, everyone. Welcome back to E304. Today we're going to continue talking about this concept of quantum confinement or trapping of electrons. And we're going to specifically talk about the difference between conductors and semiconductors. When it comes to quantum confinement or electron trapping. And it turns out that because of the material properties of conductors and semiconductors, these behave just a little bit differently. So let's start with the conductor. So what's unique about a conductor? Well, it conducts electrons, right? It has free electrons that are moving around. The bands, the valence and conduction bands overlap. So at all reasonable temperatures, we can have electrons that are available for moving current. So it can be a little bit hard to achieve quantum confinement unless let's draw some crystal lattice here. If we begin to make our solids smaller and smaller and smaller to where at least one dimension of, and so this is my picture of a solid crystal lattice, and it goes on, it's three-dimensional like so. If we bring at least one dimension of this crystal lattice to a size that's on the order of the spacing between atoms. So reduce the dimension to something on the order of magnitude of lattice spacing to approximately the lattice spacing. Well, then we can begin to confine these electrons. Okay, so we have to make this this quantum dot or quantum wire or quantum well quite small in a conductor before we can trap these electrons. And really what we're doing is we're taking away the ability for the electrons to move about if we make this dimension very, very small. So let's talk about what happens in this case. Well, essentially what we're doing is removing the electron's ability to move about, so we're turning this conductor into an insulator. So this is what's called the metal to insulator transition. So essentially what I'm saying is we're taking a metal, we're making an insulator. Well, how do we do that? So let's think about the energy bands. We know that in a bulk conductor, the valence and conduction bands overlap. So at normal temperatures, many electrons can jump right across that barrier and go into the conduction band and conduct. Well, if we have a small particle, so instead of a bulk conductor, we have a small particle, say something like 13 atoms. Well then, if we have our Fermi energy here, if we have a very small particle, then we know that the 13 splits from the 13 atoms are distributed between 0 and EF, so on and so forth. So there are going to be 13 of them. 13 of these splits. But if we focus right here, what this means is that the spacing between EF and the topmost sublevel here becomes greater and greater and greater. So this, let's call this delta E. This is the spacing. All right. Well, what does it take for an electron to hop from the valence band at this level here up above EF, so it can go into the conduction band and conduct? Well, at normal temperatures, this electron can be pushed up by let me use a different color, a factor of Boltzmann's constant Kb times T. Okay, so these are thermal vibrations at normal temperatures that allow this electron to jump up into the conduction band. Well, if delta E is bigger than kBt, then that electron can't jump. So if delta E becomes greater than Kb, which is a Boltzmann's constant, times T, then electron is stuck in the valence band. It can't go up to the conduction band, it can't conduct, and it behaves like an insulator. So this is how we get a metal to insulator transition, by simply making the particle smaller and smaller and smaller until such a time where the delta E becomes big enough that kBt no longer is enough energy to get that electron to hop. All right, so that's in metals. So now let's look at semiconductors. Okay, so for semiconductors, we have a similar drawing. Let's see if I can draw a little bit better straight line here. It's a little bit better. So again, we have energy going up this way. Okay, and for a semiconductor, we know we have the bottom of the conduction band. We know we have the bottom of the valence band. And in a semiconductor, we already have a band gap that's built in, right? And the Fermi energy is somewhere in between. Okay, well, what happens in a semiconductor, so let's label this is a semiconductor. At normal temperatures, a few electrons cross this band gap and go up to the top. So an electron goes from the valence, hops up from the valence band into the conduction band. This is our electron. And when it does that, it leaves behind an empty space where it used to be, and that empty space is a hole. And this hole is a positive charge, where the electron is a negative charge. Okay, and we know, again, remember F of E, the probability of an electron existing in a certain spot. And that tells us that there is some probability that at normal temperatures, some of these electrons will jump up to the conduction band. We can also add external energy like heat or electric current to encourage these things to happen. So when an electron jumps, it leaves a hole, and this electron and hole pair are sort of held together by Coulomb force. And this thing is called an exciton. So this electron hole pair is called an exciton, and it is held together by Coulomb force. Okay, and this electron hole pair is very, very similar to our hydrogen atom, where we have a positive charge, just like the hydrogen nucleus, proton, and a negative charge, just like the hydrogen electron. And so we can calculate or measure here what's called the exciton Bohr radius. Now, of course, we know the Bohr radius from chapter 3 is the distance between an electron and a proton and a hydrogen atom. Since this is very similar, the exciton Bohr radius is the separation, the electron hole pair separation. and this is something on the order of 2 to about 20 nanometers. Okay, so again, much like the hydrogen atom, the separation between the electron and the hole. So if the dimensions of our solid are on the order of this Bohr radius, so the physical separation between these two, okay, if the size of our solid is on the order of that separation, then we can have confinement. So confinement, right over here, confinement occurs at dimensions on the order of the exciton Bohr radius. Which is greater than the interlattice spacing that we need in the case of a metal. So semiconductors are somewhat more forgiving in allowing us to confine electrons with bigger particle sizes. But now let's talk about, well, what happens after this electron jumps up to the conduction band? Does it stay there? Well, no, it's not. That electron will eventually lose its energy and come back into the valence band. And when it loses that energy, the way it loses that energy is by emitting a photon. And the energy of that photon is the transition energy between the conduction band and the valence band. So the wavelength of that photon is exactly the energy of the band gap. So what does that tell us? Well, it tells us that if we can change the band gap, then we can change the wavelength of the emitted photon. So this has some very key and exciting implications for optoelectronics and photonics, right? So if we can change the wavelength of the emitted photon by simply changing the band gap, then we can emit different colored light. And the way that we change the band gap, of course, is by making the solid smaller and smaller and smaller, because we know the smaller the solid, the greater the band gap, to some extent.